Hello YouTube and welcome back. Here's Chapter 1, Section 3, Part B. We did questions 1, 2, 3, and 4. Now we're going to do question number 5. And here we go. Alright, so Computer Science Honors 103 continued. Let's put in what we're doing. Defining functions. And let's put in the date, 2019-09. Was it 2-4 today? And my name. Okay. All right, so here's number 5. Say your domain is, in this function, 1, 2, 3 positive integers. And the output is, we're mapping that domain onto this range, 2, 5, 10. Can you come up with a function that does that? And we figured out that if you subtract 1 from each of these numbers, 2, 5, and 10, they're perfect squares. 1 squared, 2 squared, 3 squared. So isn't it the input squared plus 1? Okay, so let's define that function. Define, I don't know, what did I call it? H of n. I don't know, whatever you want to call it. And return n squared plus 1. Let's see how that works. Show h of 1 equals, well, h of 1, and that should be 2. There it is. H of 2 should give you 5. H of 3 should give you 10. And just for fun, let's go to h of, I don't know, 9. What's h of 9? 9 squared is 81 plus 1 is 82, just for fun. And we graph that's probably parabolic, and that's number 5. We skipped 6 and 7 because it was a question not covered in the chapter, really. So let's go to number 8. All right, so let's put a blank show here just for fun. Okay, show number 8. All right, so what if your domain is -1 to 1? Now, notice, I'm not saying, notice how this is different. Yeah, not just saying that. That means negative 1 is less than or equal to x is less than or equal to 1, right? This is strictly less than. -1 is less than x is less than 1. It doesn't include the -1 or the 1, right? So my domain doesn't include -1 or 1. Anything in between, and it doesn't include anything outside -1 or 1, right? And of course, you know this notation. This is called a semi-open, where we're not including -1, but we are including positive 1 and everything in between. And this is called a semi-closed interval, where we're including -1, but not the positive 1. And this is a closed interval. We're including both the -1, both endpoints, -1 and positive 1. And this is an open interval. That's what they want. So that's the domain, okay? We're mapping that onto all real numbers. All right, so from -infinity to positive infinity. How are you going to do that? Well, we played around a little bit. We said, okay, what if we let f of x, whoops, what happened there? Oh, my quote's messed up. Whoopsie. Okay. All right, so what if we let f of x, f of x equal, I don't know, 1 over 1 over x minus, how about 1 minus x? 1 minus x. So what does that mean? Well, you're going to have a vertical asymptote at x equals 1, so it's not going to include 1, right? Let's show that. Okay, but it doesn't include anything after 1, doesn't include anything less than 1. Remember, x min, x max default to -1 and 1. So I want to see what's going on beyond that interval, see that we're not getting that domain, we're not using that domain. So how about we go from, I don't know, -5 to +5. Let's just see what it looks like. All right, so definitely not defined at 1. Remember, that's an artifact, that vertical line there, that's not really there. But we're getting some y values over here. I don't want y values outside -1 to 1. They're getting y values here too. What are we going to do? Or how about this? we don't want -1, we don't want +1 either, right? Let's deal with that. What if we make the fraction with a denominator of 0 for both x is 1 and x is -1? So this should have vertical asymptotes at +1 and -1. And they do. If you want to restrict the y values, remember how you do that. You have to say this is x min, you got to say this is x max, otherwise that's optional. Then you got to say what your y min, y max is. It's something small. Y min is -10, small meaning near 0. Y max is, say, 10 or whatever you like. Even 5. Why not 5? Oops. Equals. Stop it. Okay, let's see what we got. All right, so again, these vertical lines are artifacts. They're not really part of the graph. So this is defined between -1 and 1. And we're getting y values, all y values from -infinity to +infinity, except for 0. Well, wait a minute, we're not getting from 0 to 1. Nothing's being graphed on this range. That's weird. And we played around with this a little bit, and we said, okay, what if we divide by the square root function? How about the square root of that? That would restrict the domain, wouldn't it? Okay, now look what it's saying. It can't plot outside 1 and -1. I told it to plot from -5 to 5. Notice it can't. So that killed off that part of the domain. So I think we're okay from -1 to 1. I'm going to do that. -1 to 1. Okay, that's good. But wait, I'm only getting a range where y is greater than or equal to 1. What are you going to do? Well, that's if I have a +1 here. What if I have a -1 here? Well, that would be a reflection across the x-axis, and now my domain is, my range is all y is less than or equal to -1. I'm not getting what I want over here. All right, what if I don't just put -1 or +1 there? How about if I put any old x of any old sign I feel like? How about that? Would that help? There it is. So look, you're getting all the y values. As x approaches 1 from the left, y is approaching +infinity. As x approaches 1 from the right, y is approaching -infinity. And we're getting all these values between -1 and 1 for y, which we weren't getting at some point. And so I think that's it. So we're just playing around. Oh, we should probably show the function just for fun. Make the output easy to read, because that's what we graph. There you go. Well, they factored it out, but there you go. That's what computer algebra system does. It gives you your expressions in simplest rational fractional form, right? So there you go. Okay, I like it. All right, that's number 8. All right, show blank line. Show number 9. Oops. All right, what's the number 9 about? Oh, compositions. Okay. They said, what if f of x is 2x plus 1? Okay. So let f of x... All right, okay, this is what they want. They want to find f of g of 1 and g of f of 1, given that f of x is, what was it now? 2x plus 1. And g of x is, what was g of x? X minus 1. Can you calculate the composition f of g of 1? And likewise, g of f of 1. Well, I'm just going to copy this. All right, let's see what happens. And so what does that mean? Well, that's a composition of functions. G of f of g of 1 means take 1, plug it into g, which gives you 1 minus 1 is 0. And take that answer and plug it back in. 0 times 2 is 0 plus 1 is 1. Fine. Notice this is not usually a commutative operation, the composition of two functions. So what does g of f of 1 mean? Take 1 and plug it into f. So 2 times 1 is 2 plus 1 is 3. And plug that into g. 3 minus 1 is 2. There you go. And just for fun, if you want, how about we did f of negative 1? How about that? Let's play with that just for fun. How about, whoops. How about g of 0? What's happening? Let's see if we can do that composition. Just making up some more problems. I didn't ask for that, but there you go. Just for fun. So f of negative 1 means plug in negative 1 into f. So negative 1 times 2 is negative 2 plus 1 is negative 1. And then plug that back into f. Negative 1 times 2 is negative 2 plus 1 is negative 1 anyway. Okay. What if we do g of 0? Take 0, plug it into g. So 0 minus 1 is negative 1. Take that answer, plug it back into g. Negative 1 minus 1 is negative 2. Perfect. Okay, so you can do any old composition you want, algebraically or numerically. This is mainly numeric. All right, and 10. 10 is saying, is this a true statement? Can you show that this is a true statement? That if you add the first n consecutive odd integers, where n is odd, well, up to 2 times n. So if n is 10, we're going up to less than 20, but only the odd integers, So that goes up to 19, in other words, right? So technically it's up to there. Equals n squared. So in other words, if I do n is 3, I get 3 terms. We're going up to 5, right? And we get 1 plus 3 plus 5 is 9, but isn't that 3 squared? Ah, okay. So let's show this. Show that what happens. What's 1? Well, that's silly. It's 1. Okay. But what's 1 plus 3? 1 plus 3 is going to be 4, which is 2 squared, right? All right. What's 1 plus 3 plus 4? 1 plus 2 plus 5, adding the odd integers, consecutive odd integers. And so you get 1, 4, 9. You get perfect squares, don't you? Right? So that sort of makes sense. Another way to play around with it is to write a function. Define, how about sum odd of n? How about we show how are we going to do this? Well, if we show, let's play with this. If we show range of, I don't know, n, what do you get? Let's try this. So let's say I do sum odd, let's see, show, quote, comma, sum odd of 3. I should get 9, right? But I don't. What I get is a list of, whoops, I didn't return it, sorry. I didn't mean to show here, I mean to return. Okay. So what you get is a list of integers, 3 integers starting at 0, so it's less than 3. But those are consecutive even integers. How do you make it not start at 0? I want 1, 3, 5. And how do you make it skip by 2, so it's 1, 3, 5? Ah, well, you could do 1 comma to say where to start instead of 0. So instead of 0, 1, and 2, it'll just be 1 and 2. Right? Now I don't want 1 and 2, I want 1 and 3 and 5. So how did we fix this? Oh, go up to 2n. Ah, yes, okay. So if you do this, comma 2, it'll skip by 2, so 1, 3, 5. But the thing is, it's going to stop at less than or equal to 2. So that's where the 2n comes from. Oh, okay. So up to 2 times n. Here we go. Let's see. That's 1 through 5. And that's going to be, whoops, that's the list, right? But I don't want that. I want the sum of the list. Oh, okay. So how about if we show that So we can see what the list is. Let's show that. But since it's a list, remember the list data structure in Python has a sum command. So let's do the sum of the list, which is really a series, the sum of a sequence, right? All right, let's see if that works. So, oops, what did I do? Line 27. Oh, I didn't close. Oh, I need a parenthesis for the show. Ugh. Silly me. All right, so the show prints out the list, but the sum function prints out the sum, which is, if you're doing the first 3, you get 3 squared. If you do the first 4, which includes 7, we get 4 squared, and so forth. Ah, that's it. I like it. So let's do this. Sum 1. Sum 2. Let's see what you get. All right, so sum 1 is 1, sum 2 is 4, sum 3 is 9, right? Okay, so sum 4 would be 16. 4 is the number of terms we're adding up. We're returning the sum of the series, right? So let's do 4 should give me 16, which is 1357. And sum 5, for fun, should give me 25, which is 1 plus 3 plus 5 plus 7 plus 9. Let's see if that's right. Which is 25. There you go. Perfect. This is working nicely. All right, let's go crazy. What if we make it, just for fun, 50? The first 50 odd integers add up to 50 squared is 2,500. And there they are. There you go. Perfect. Nice. I like it. Oh, let's make it fit on the screen. How about 20? Would 20 fit? Is that a problem? I could zoom in, zoom out, I guess. That's fine. So the first 20 odd integers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, starting with 1, add up to 20 squared is 400. Yeah, it works. I like it. So that's the output for number 10. Make it a little smaller. There you go. There's the output for number 10. Here's the output for number 9. There's the output for number 8. There's the output for number 5. There's the code for number 5. There's the code for number 8. Code for number 9. Code for number 10. Okay, I think that covers it. All right, have a good day, YouTube. Hope that was helpful. Bye-bye. Welcome back next time.